Hi listeners, welcome to the video lecture series on power electronics, and this video is a continuation of buck converter derivation video of the previous lecture. Let us go into the video directly. In the previous video, we have derived the expressions for this 5 till inductor ripple current, and now let us try to derive the expression for maximum inductor current and minimum inductor current. Let us go into the derivation. So the sixth part of the derivation is to find the maximum value of the inductor current, that is ILMAX. If you look at the graph here or the waveform which is given here, the ILMAX is nothing but this IL average plus delta IL by 2. So I can write IL average, ILMAX as IL average plus delta IL by 2. But this IL average, if you look at this IL average is nothing but I0. I0 is the load current. So IL max, I can write it as I0 plus delta IL by 2. So this is being taken from this waveform. If you look at this is I0 plus this delta IL by 2, you will give me IL max. So let it be the next expression number 8. So this is expression number 8. Similarly, the seventh part of the derivation is to find IL minimum. If you look at IL minimum again from the same graph or same waveform, I can write I0 minus delta IL by 2. So this green line is I0 minus this delta IL by 2 is IL minimum. So I can write I0 minus delta IL by 2. So this is the expression for the minimum value of the inductor current. So these two expressions are also important for further derivations. I have taken these two expressions and written here for further simplification for further derivation. The next part of the derivation is we have calculated the value for minimum and maximum value of the inductor current, and now let us go into the expression for source current. Source current can be calculated. This is the 8th part of the derivation. Source current can be calculated by putting input power is equal to output power. That is assuming that there is no losses present in the system. Power electronic systems are generally used to minimize the losses. So that is why we are equating that input power is equal to output power. Input power, if you look at, this is what I call it as source current IS. IS is the source current. So Vs into Is is the input power, which should be equal to output power is V0 is the voltage across the load and I0 is the current. So V0 into I0 is the load voltage and load current. So once from this I can simplify and find out Is is equal to V0 into I0 by Vs. So this is the expression for the source current. This is the primary expression, but anyhow this expression can be further simplified. We can replace this V0. V0 is nothing but D into Vs. Look at this expression 5. So once I replace this V0 with D into Vs, I can get D into Vs into I0 by Vs. So this Vs and this Vs will get cancelled. So this and this will get cancelled. Finally, it is left out with D into I0 by D into I0, which is equal to Is. So this is also another expression for Is. This is expression number 10. So let me try to write this expression 10 here for easy understanding of the further derivation, which is equal to D into I0. We have derived the expression for source current, and the next is we are going to derive the expression for switch current, which is average and RMS values of the switch current. If you look at this circuit diagram, the switch current and source current both are same. That is SW and S are both are same. Let me try to mark it as SW for meaning of switch. Switch current and source current both are same because whenever this switch is turned on, then only current will flow through this switch, which is equal to source current. But very important, this source current is equal to D into I0. If I assume that I0 is constant, because current through the load should be constant. If I assume that I0 is constant, which is equal to IL average, because IL average is constant, is fixed. I0 is fixed because IL average is fixed. For a particular duty cycle, source current is also fixed. So let us assume that I0 is fixed. When the current will be flowing through the switch only when it is in on condition. When the switch is in on condition, only during the one part, that is till DT, the switch is in on condition. Then it is in off condition for 1 minus D into T. So this is the duration where switch is in on, and this is the duration where switch is in off. Let us assume that the current through the load is constant. It is constant and let it be I0. So when the switch is on, there will be some amount of current flowing through it. So let that current is equal to I0 because that is the current which is going through the switch also. So this current, if you look at the current through the switch, it will be flowing through the switch only when it is in on condition. So let me try to draw it here. This is the duration where switch is in on condition. So this I0 will be flowing through the switch for this duration, and for the next remaining duration it will be in off condition. So there will not be any current flow. So I want to find the average value of this this current. So this is 1 minus D into T, and the on time duration is T. So if I want to find out the average current, I want to find out this area divided by the total time. So the ISW switch average current is given by the current I0, this area. I want to calculate this area. You can see that this is the area which I am trying to calculate. So which is I0 into dt, because it is a rectangle, length into breadth. This is height is I0 because that is the current which is going to flow through the switch, multiplied with this breadth which is dt, divided by the total duration. From this to this it is t. So the total duration is t. So if you look at the average value of the switch current is ISW average is equal to D into I0. So this is the average current which flows through the switch. Let it be expression 11. Similarly, the RMS current, that is ISW RMS value of the current which is flowing through the switch is given by square root of area under the squared curve. So that becomes I0 square into dt by t. So this t and this t will get cancelled. So ISW RMS is equals to, I can take this root out, I0 into root of d. This is the expression for RMS value of the switch current. To find out the average and RMS value, you can just look into the unit 2 second video, which will give you very clear understanding of RMS and average current calculation for any waveform is concerned. The switch current waveform, I can even mark it here. This is the duration where switch is on. So this current will flow. During this part, the switch is off. So this current will not flow. Again, this current will flow. So this is the current which is going to flow through the switch. So this is what I have drawn here. So that is what I have calculated the average and RMS values. So we have calculated switch current, and the next part of the derivation is we are going to calculate the diode current average and RMS values. Let us look into the diode current expressions. If you look at the modes of operation, the diode will come into picture only when the switch is in off condition. That is, when this switch is in off condition, then only the diode will be taking current, will be having current through it. So if you look at, this is the point where the diode is turned on, that is when switch is off. So from this point till this point there is no current. From this point the current through the diode is this I0, and again from this point to this point there is no current. Again the current through the diode is I0. So this is what the current which is flowing through the diode. So now if you look at, this is dt and this is 1 minus t into d into t, or it is completely called as t on plus t off. So now I need to find the average value and RMS value till this point. This is capital T. So if I try to find out the average and RMS value, this is the 10th point of the derivation. Look at this characteristics. This is I0 multiplied with 1 minus d into t. this 1 minus d into t is only t of, not total t. So 1 minus d into t is only t of. So I can calculate I diode average as the current I naught into the duration of the current is 1 minus d into t. It is 1 minus d into t. This is the duration for which the current flows through the diode divided by the time period t. So this becomes I naught into 1 minus d. This is the expression for diode average current. Let it be expression number 13. Now again, diode RMS current of the diode, ID RMS, for which again you put I naught square, squared root of area under the square curve, 1 minus d into t by t. So everything within the root. If I simplify this, I will get I naught into this t and this t will get cancelled out. This and this will get cancelled out. It is left out with 1 minus d. This is the expression for RMS value of the diode current. So this is expression number 14. The remaining part of the expressions we will derive it in video part 3 of buck converter. Thank you for your patient listening. Thank you.